Problem 5, you're given a situation where you've got a wider tube and a narrower tube, as we did in class. And you're given the information that if you put water in this tube, enough water to fill the tubes to some height, but not so much water that you overfill the narrower tube, so that the water will rise to a certain height when you invert the tubes in one direction, so that all the water is in the wider tube, and it doesn't all fill the narrower tube when you turn it over, invert it in this direction. So that we have the information that when the water is sufficient to fill 4 centimeters of the wider tube, it fills 9 centimeters when inverted, so that the water is in the narrower tube. So there's our information. Now, the question then was posed: if you have water flowing in at a constant volume rate, same amount of volume for every unit of time, is water rising faster when it's in this tube or when it gets into the narrower tube? Okay. Now, if I let this arrow represent how fast water is rising in the wider tube, then I've got an arrow here that's going to represent how fast the water rises in the narrower tube. Should this arrow be shorter or longer than this arrow? Okay, now the question that is actually posed is, if the water is rising in this tube at 3 centimeters per second, how fast is it rising when we get to this tube? Again, the same amount of volume every unit of time is entering from here, and the water will eventually get up to the point where it's rising in the narrow tube. So if it's rising at 3 centimeters per second when it is still in the wide tube, how fast does it rise once it gets to the narrow tube? Now, first question we could ask, we could break the thing down like this, and we ask, is it going faster or slower in this tube? You should pause and see if you can answer that question. Well, hopefully you've done so. Another thing we can think of, though, is that, well, we still know that 4 centimeters of height here gives you the same volume as 9 centimeters of height here. So wherever 4 centimeters is, and we can draw this to any scale we want, if 4 centimeters, and I wrote that as meters, let me corrected that and decided to write this in a different color because I want to shade this region of the large tube. Okay, 4 centimeters here of height corresponds to a certain volume in this tube, and the same volume would occupy 9 centimeters over here, so that a 9 centimeter segment of this tube would contain the same volume. That's the information that we have. Now, it takes a certain amount of time to fill this 4 centimeters. So whatever time it takes to fill this 4 centimeters, in the same time, you're going to fill this 9 centimeters. So we can make the statement, in the time required to fill 4 centimeters here, water is going to rise 9 centimeters up here. Now, how does that inform your answer to this question? Is your answer the same as it was before? And then the question, of course, is, in which tube is water rising faster? Okay, well, you should think this through, but the question is now, what are the relative speeds? How fast is water rising in the narrow tube compared to the speed with which it was rising in the wider tube before it reached the narrower tube? Well, from this statement that water takes the same time to rise 9 centimeters in the narrow tube as to rise 4 centimeters in the wider tube, we conclude water rises 9 centimeters in the thinner tube in the same time to rise 4 centimeters in the wider tube. So it must rise how many times as fast in the thinner tube? Well, that would be 9/4 as fast. 9/4 is 2 1/4, a little over twice as fast in the thinner tube. So how does this arrow relate to this arrow? If these arrows represent the speed, this one's going to have to be longer. It's going to have to be 9/4 as long. So our speed arrows, if this arrow is this length, well, this arrow is going to have to be longer than it was drawn here. It's going to have to be 9/4 over twice as long. Okay, maybe I've got that a little bit too long, or this one a little bit too short, but you can adjust that. Okay, well, here is a reasoning process, but then the conclusion ought to be fairly obvious that water has to rise 9/4 as fast in the thinner tube under these circumstances. So if the speed of the water rising in the wider tube is 3 centimeters per second, what has to be the speed in the narrower tube? You should think about that and work it out. And it should be fairly obvious. It's got to be 9/4 of 3 centimeters per second, which is 27/4 centimeter per second, or, well, that's 6 3/4, 6.75 centimeters per second. So now we have, well, we can just go back to our original information. We have two cylinders here, the cylinder occupied by this water and the cylinder occupied by this water. They have the same volume, but this one has 9/4 of the altitude. What does that tell us about the diameters and or the cross-sectional areas? Think that through for a minute. Okay, well, we know that the most direct relationship here is the one that comes from the fact that the volume is the product of the cross-sectional area and the altitude. Now you could use the fact that the volume is pi r squared h, but that's much less direct. This is more fundamental. This is simply an instance of this, as we've talked about. This is the fundamental idea. For any cylinder or prism, any shape with uniform cross-sectional area, that's what you have. Okay? Cross-sectional area multiplied by the altitude, and you should understand volume well enough to understand why that has to be the case. Now that's a little bit difficult. You should work to understand volume well enough that you automatically understand this and are able to explain it. Okay, so we have this, and we know then that the cross-sectional area, or the altitude of one is 9/4 as great as the other. The volumes are the same. What does that say about the cross-sectional areas? Hopefully you figured this out without any further hints, but I'll say ACS times H, which is the volume, is the same for both. This one has 9/4 of the altitude. So, how would the cross-sectional area of the narrower tube compare with the cross-sectional area of the wider? Well, the answer is it has to be 4/9. Because if you multiply 4/9 as great by 9/4 as great, you get the same result. Now we could write that out algebraically, and I probably will as an addendum, but that should be common sense. You should understand the algebra, you should understand the proportionalities, or work to understand the algebra and proportionalities well enough that that becomes a simple and straightforward conclusion. Now if pi r squared for the narrower tube is 4/9 as great, as it must be because pi r squared is the cross-sectional area. If pi r squared is 4/9 as great, then r squared has to be 4/9 as great. Pi is the same both ways, it's only the r squared that can change. So r squared for the narrower has to be 4/9 as great as r squared for the wider. Now, if r squared is 4/9 as great, then how does r compare? Okay, here's our situation then. For these cylinders, same volume, the height of the narrow has to be 9/4 greater. That 9/4 is great as that of the wider. So the cross-sectional area of the narrow has to be 4/9 that of the wider, since the volume is the product of cross-sectional area and height. I'm using height for altitude. Altitude's the better word, but we understand what I mean, I think. Well, the cross-sectional area is pi r squared, so pi r squared for the narrower is 4/9 that of the wider, which means then that r squared for the narrower has to be 4/9 that of the wider. So what does that tell us about the relationship for the radius of the narrower? Well, reasoning leads us to the idea that r for the narrower has to be square root of 4/9. Since r squared is 4/9, r has to be the square root of 4/9, which turns out to be 2/3 that of the wider. Okay, now this reasoning is sort of intuitive, and it's probably not as clear as it would be if you'd worked it out algebraically. So let's work it out algebraically. We're going to use n for narrow, w for wide. We know that the height of the narrower is 9/4 the height of the wider. That goes back to the original tubes, which we inverted. 9 centimeter height here gives you the same volume as 4 centimeter height here. The volumes are the same because it's the same water in both. And the water occupies the same volume. It's not very compressible, practically incompressible. It tells you what? Well, volume is cross-sectional area times height or altitude, so that the cross-sectional area times altitude for the wider equals the cross-sectional area times the altitude for the narrower. It follows then that the ratio of the cross-sectional areas, now we could do this narrow over wide or wide over narrow, but here we did narrow over wide, so that's what we're going to do here. We just solve this. We solve, divide by a cross-sectional narrow here, and then divide by h narrow here, and we get this. Of course, we've got to switch sides, but we know we can do that. So this relationship is easily rearranged to give us this. And then the height of the narrower, remember, is 9/4 the height of the wider. So height of the narrow is 9/4 height of the wider. And we simplify this expression. Height of the wider gets divided out. The 9/4 gets inverted. We get 4/9. Now, how would we proceed to get the ratio of the areas? What would the detailed steps be? You should write that out and then check what I get. Okay, well, my first step would be to take these cross-sectional areas and replace them with pi r squared. Pi r n squared for the radius of the narrower squared for the cross-sectional area of the narrower, and pi rw squared for the cross-sectional area of the wider, and that should equal 4/9. And then, of course, the pi's divide out. Okay, pi over pi is 1, so you just end up with rn squared over rw squared equals 4/9. So what we want, though, is the ratio of the radii, not the ratio of the squared radius here to the squared radius here. How are we going to get that? Well, the algebra is really straightforward. Rn squared over rw squared is Rn over rw quantity squared. That should be 4/9. So Rn over Rw would have to be the square root of 4/9. I could say plus or minus the square root of 4/9, which would be the official result here, but the radius can't be minus, so we don't worry about that plus or minus here, but we get 2/3, so that Rn is 2/3 of Rw, and we've got it. Now, I would definitely hope that you'd be able to follow this reasoning and reconstruct it yourself, and this type of reasoning in other types of problems. Having done this, this type of reasoning should become very intuitively clear to you. And this is a very important type of reasoning. This is formal. This involves symbols. This involves understanding and intuition and experience. So I hope you gain that.